So we saw how to allocate memory to processes and how to run programs. As a second concern, we want to allocate main memory to ensure that a maximum number of processes can be accommodated. Achieving the efficient memory management involves addressing specific requirements, which we can group them in 5 main titles: relocation, protection, sharing, logical, and physical organization. In the relocation, we see a dynamic relocation, and it's the capability essential to adjust the base address of a process as needed and accommodating changes in size or position. In protection, uh, implementing memory protection mechanisms uh, is crucial to protect the integrity of each process's memory space and prevent unauthorized access. In sharing, we want to support memory sharing among processes to enhance resource utilization by allowing multiple processes to access the same memory concurrently. In the logical organization, we try to structure memory logically, and it's important for facilitating efficient access and management, defining how processes perceive and interact with the memory space. Okay, and the last one, physical organization. Actually, efficient physical organization at the hardware level ensures that processes can be loaded and executed with minimal overhead. To sum up, addressing these requirements is fundamental to creating a robust memory management system, and it promotes optimal resource utilization and dynamic adaptability to varying process needs. So before move on much details about memory management, we need to first learn address spaces. So addresses are something very essential in memory management. Let's explore the different types of addresses. There are actually two types of addresses used in memory management: physical and logical addresses. So physical addresses represent a direct location in main memory, the address seen by the memory unit, and actually this is the actual location on physical memory. Where data is stored or retrieved. Uh, on the other hand, logical addresses are generated by the CPU, and they are also known as a virtual addresses. It refers to a memory location independently of the physical organization of memory. So logical addresses are used by compilers, by CPUs, and they provide a level of abstraction from the physical memory layout. Lastly, relative address is a kind of logical address expressed as a location relative to some known point in the program. Uh, it offers a convenient way to express addresses in relation to program structure. So in summary, logical addresses are the addresses used within the program's code, and they are independent of the physical memory layout, whereas physical addresses are specific and physical location that can be referenced. So in a computer system, we translate logical addresses into physical addresses using a dedicated hardware, dedicated hardware device as known as the memory management unit. So let's explore the functionality of the memory management unit. The MMU is designed to map logical or virtual addresses to physical addresses. In MMU scheme, a key component is the base relocation register. Yeah, base register. The MMU adds the value in this register to every logical address generated by a user process when sending it to a memory. The process of adding the base register value to the logical address effectively translates the logical address into a real physical address. So the user program interacts with logical addresses exclusively, and it remains unaware of the actual physical addresses. Actually, from the user's program's perspective, memory management unit transparently handles the translation to physical addresses. So let's look at this diagram. It shows system elements such as bus, memory, and this controller. Here, both CPU and memory management unit components housed within the CPU package. Simply, the memory management unit is responsible for sending physical addresses to the memory, while the CPU sends virtual addresses to MMU. So there is an example of logical and physical address spaces for two processes in a computer system. So process one, let me take this color, the purple one. The process one has a logical address space represented on the left. So the base register is set to 500K and the length is 350K, okay? In the right side, we see process 2's logical address space, and the base register for process 2 is set at 200K and length is 300K, okay? And in the middle section, we try to illustrate the computer's physical address space. The allocated regions for process 1 is in this region, okay? And for process 2 is in this region. This means that process 1's logical address space spans this area, 500K to 850K. Consequently, process 2's logical address space spans this area from 200K to 500. Here you can understand how base registers and lengths determine the boundaries of these address spaces.